Hello. In this exercise, we're going to be using multiple regression techniques to understand the age of death of a number of 19th and 20th century statisticians. The predictor variables that we're going to be using are their birth year and their death year. Now, of course, this isn't really a type of problem that would typically involve multiple regression because we can get a very good approximation of the age of death of any of these individuals by simply taking the birth year away from the death year. Of course, there will be a little bit of uncertainty depending on whether they die before their birthdays or after their birthdays, but it's still a very close approximation. However, we'll use this multiple regression just so that we can actually look at the overall process. And here are the data that I've read in. There's a variety of statisticians here listed in this data set. It's a common delimited file. And the first thing that we should do is simply plot a graph of the age of death according to a certain predictor, and this is what we're going to be looking at here. So let's have a look. Here's the date of birth of the statistician, and here is the age, and we've simply called up a plot using text here to give the individual titles, just so that we can actually see the labels here underneath each of these points. Now, what we would like to do first of all is to begin to explore what predictor variables might influence that response. Now, typically we'd jump straight to the multiple regression, but here we're going to take it in smaller steps. So first of all, I'm going to fit a model, and it's going to be a simple linear regression model of the age of death and see how it might depend on the birth year, the date of birth. Well, we fitted the model using the LM routine, and here is the analysis of variance associated with that model. And what we can see here is that there is no evidence to reject the null hypothesis that age and birth year are entirely independent of one another. We can't reject the null hypothesis that the population level coefficient is 0, because we have a relatively high value of significance probability. So now let's move on and actually look to see whether the death year might influence the age on death. So here we're going to fit another linear regression model with age on death and to see whether it might be dependent on the death year. So here is the analysis of variance table after fitting that simple linear regression model. And here we see that we can indeed reject the null hypothesis that there is no relationship between age on death and death year, in that the probability of us obtaining that test statistic, or a more extreme if the null hypothesis is true, is really very small. So we have evidence that there is a relationship between death year and age on death. What way does it look? Well, we can simply ask for the coefficients, and it seems that from the gradient here of 0.147, it appears that the age to which these statisticians were living tends to increase with the year of death. Now, let's just go a step or two further. Let's have a look at the fit of a proper multiple regression model in which we fit both predictors, both death year and birth year, and see their combined role on the age of death. And here is the fit of the model, and here is the analysis of variance table. Now you'll note that here we're using type 1 sum of squares by default in R, and it seems that both death year and birth year in these cases are both highly significant. Well, why has birth year gone from low significance here, so not really very significant, to very highly significant? We have to bear in mind that with a type 1 sum of squares, we are controlling for the effects of other predictors above it in the list. And so here, when we're looking at the effect of birth year on the age of death, we are controlling for death year. So the birth year does indeed have a relationship on the age of death once we can control for death year. You'll note also that the significance of death year has improved considerably. Why is that? Because we're not controlling for birth year at all. Well, we're not controlling for birth year, but we are affecting our overall estimate of the error variability in our data by adding new terms. And so it happens in this case that the significance of both individual predictors have gone up. Let's have a look at the coefficients here, and here we see something that we were sort of expecting already. The coefficient for death year is approximately 1, and the coefficient for birth year is approximately -1. And here we'll note that the intercept is something about 6, but remember these values here are in their thousands, so this intercept really won't have very much effect at all. So what we're seeing here is that very approximately the age to which the statisticians lived, and of course we're trying to make wider inferences about statisticians in general, we can simply take their death year and birth year and take the birth year from the death year, and we will have approximately how long they lived. So we're getting something reassuringly intuitive from the fit of our model. Now, I'm going to load the library car, which has got a type 3 sum of squares. And you remember a type 3 sum of squares simultaneously adjusts for the effects of all of the predictors in the model. So what we're going to do is, with that model 3 that we have just fitted, ask in this case for a type 3 sum of squares partitioning. And here you'll see quite clearly that both death year and birth year have a very highly significant effect on that response, age of death, once you control for the effect of the other variable. Now it just remains to evaluate the underlying assumptions in our models. The first thing we should be doing is simply testing for homogeneity of our residuals, and that looks pretty good when it comes to evaluating. What about now looking at the normality of those residuals? Well, here we have something of concern. If we really wanted to make inferences about the lives of statisticians rather than simply treat this as an exercise, then that QQ plot really does suggest that we have got relatively non-normal data. Let's have a look at this in terms of just looking at the histogram. Here is the standardized residuals from that fitted model, and we can plot them out. So it looks something of a bivariate distribution, although we should bear in mind that we're not currently dealing with a great deal of sample data here. So if we were going to make important inferences about that population, other than treat this as a simple teaching exercise, then we would have to do something about that problem of lack of normality. And of course we'll get onto those sorts of problems later on. Thank you for listening to this R Labs tutorial video. If you found this useful, you might be interested in our free online Moodle course, or check out and subscribe to our YouTube channel.